How does the saturation level of a solution affect the growth rate of crystals? I performed hands-on research on crystals in my polymer science classroom. We attempted to grow the most rhombic and largest crystals out of a copper-2 sulfate in distilled water solution. However, we did not make measurements or take notice of the saturation levels of our solutions. As mentioned before, my polymer science class did not worry about saturation level. Instead, we just added an arbitrary amount of copper-2 sulfate to water and continued with the experiment. However, the thought occurred that the level of material we put into the water must affect the crystal growth that resulted from it. As this idea arose, I realized it would make an excellent topic for my work sample, a method in which to prove my ability to apply my knowledge and satisfy my own curiosity. In this experiment, I used both qualitative and quantitative observations to compare the growth of crystals. These crystals were made using an aluminum potassium sulfate in distilled water solution. The observations took place over 3 days in 24-hour periods at 4:30 each day. Materials used: aluminum potassium sulfate 21.5 grams, distilled water 240 milliliters, digital balance, scupula, microwave, 3 beakers, 3 plastic cups, and 3 stir sticks. The low saturated solution used in this experiment was created by saturating 3.5 grams of aluminum potassium sulfate into 80 milliliters of distilled water at room temperature. To find my medium saturated solution, I filled another beaker with 80 milliliters of distilled water and I heated it for 30 seconds. Then I added 10.5 grams of aluminum potassium sulfate to the distilled water and stirred the solution until the chemicals had fully saturated. In order to choose my high saturated solution, I performed the same process before, but I microwaved the 80 milliliters of distilled water for 60 seconds and added 17.5 grams of aluminum potassium sulfate to the solution before stirring it to the point of full saturation. Day 1, low saturation solution. After the first 24-hour period, the room temperature saturated solution had no crystal growth throughout. Day 1, medium saturated solution. After the first 24-hour period, the medium saturated solution contained a very small amount of crystal growth. Day 1, high saturated solution. After the first 24-hour period, the high saturated solution had a large, irregularly shaped crystal in the bottom of the beaker. Day 2, low saturated solution. After the second 24-hour period, there were still no crystal growths in this solution. Day 2, medium saturated solution. After the second 24-hour period, there was not much crystal growth except for a thin layer of crystals covering the bottom of the beaker. Day 2, high saturated solution. After the second 24-hour period, there was not much of a change in the solution, which I believe was caused by the fact that the crystal had absorbed most of the aluminum potassium sulfate in the solution. Day 3, low saturated solution. After the third 24-hour period, the solution continued to have no crystal growth as before. Day 3, medium saturated solution. After the third 24-hour period, the solution had formed a layer of crystals on the bottom of the beaker that was much thicker than the day before. Day 3, high saturated solution. After the third 24-hour period, the crystal in the solution remained the same size as it was the day before. Final results. There were 0 grams of crystals in the low saturated solution, 3.5 grams of crystals in the medium saturated solution, and 10.9 grams of crystals in the high saturated solution. Conclusion. Based on these observations, it is reasonable to conclude that my hypothesis was correct. The solution does produce different levels of crystal growth based on the saturation level, and the higher saturated solutions grow more massive crystals than the low saturated levels.